Okay, we're going to talk about a special class of functions called inverse functions. Okay. Two functions, f and g, are inverse functions if, when I compose them, f composed with g, it's like they cancel each other out. So with the thing I got in, x is the thing I get out. And I must be able to do it in either direction. So f composed with g of x equals x, g composed with f of x equals x. And in this case, we want to be able to note that g is the inverse of f. So we write it f inverse of x. Okay. Now, this comes with warning number 17. Do not confuse this notation as exponential notation. So this most definitely does not equal 1 over f of x. Okay. Because this is a function, this is not something we can put an exponent on in the traditional sense. Now, let's do an example. I have two functions and I want to verify that they are in fact inverses. So I have to do two different compositions. F composed with g means I take f and I'm going to plug g of x into it. So this is really this. And now I'm going to clean it up and hope I get x. First I notice that these 5's cancel. Then I notice that the -8 and the +8 cancel, and I'm just left with x. That is, however, not enough to guarantee inverses. You have to check both. And if you don't get both, then they are not real inverses of each other. So now I'm going to do g composed with f, which is that I plug f in to g. So I end up with this. Notice the +8 and the -8 cancel, leaving 5x over 5. The 5's cancel, leaving x. So because both compositions just gave you out x, f of x and g of x are inverses. Now I want to show you something a little bit interesting about these. If you were to graph f of x and g of x, I'm just going to do a really quick graph. Okay, this has a y-intercept pretty high and a pretty steep slope. This one has a y-intercept that's a little negative and a fairly shallow slope. Will look like this. Okay. Notice that if I draw in the line y equals x, these graphs are reflections of each other about the line. So if I take the pink one and reflect it about the green line, I get the orange one, and vice versa. That will always be true for the graphs of inverse functions. Okay. Now, that brings us to an interesting point. This means that if the pink one is a function, meaning passing a vertical line test, the orange one will end up having to pass a horizontal line test. Okay. Remember, we called such a function one-to-one if it passed a horizontal line test. So this tells us that not every function will have an inverse. And we're going to come into in a second what to do to determine if it has an inverse and how to fix it if it doesn't. So, to find an inverse, there are 3 easy steps. The first is to switch x and y. The second is to solve for y. And the third is to evaluate if it is a function. So, we're going to do this on 2 different examples. Okay. Notice there is no y here, but I said switch x and y. That's because when you're doing the procedure to find an inverse, we would rather write y instead of f of x. So now that I have y in, I'm going to do my first step, which is to switch x and y. Then I'm going to do whatever I need to in order to solve for y. So this is y is the cube root of x plus 1. Now, is that a perfectly good function? Meaning, if I plug in an x, do I automatically know the answer? And I say yes. So f inverse is the cube root of x plus 1. Now, I'm going to look at this example. I'm going to do the same procedure. So first I'm going to write y in place of f of x. Then I'm going to switch x and y and do whatever I have to in order to solve for y. So first I subtract 3, then I divide by 4, and here's where I run into an issue. I can solve this. This is y equals plus or minus the square root of x minus 3 over 4. But this is clearly not a function because of this plus or minus sign. So I have a little bit of an issue. So I'm going to take a step back. I'm going to think about the graph of the original function. Looks like a parabola. So clearly it's not going to have an inverse, it's not one-to-one. But we have a trick called restricting the domain. If you only look at half of this graph, this half right here, then it will pass a horizontal line test and it will have an inverse. We can imagine its graph from flipping it across the y equals x line. And in that case, the inverse would just be plus this square root. So even though this function did not have an inverse in the traditional sense, if you only look at part of the original graph by restricting the domain, you can force an inverse in a special case.